Forgot to record. Okay, well, so it's always good to come to class sometimes. My apologies I'll have to make an extra recording for those people that, so I'll put up an extra recording. I won't repeat it here for what we just did. So let me see. Let me just put a note to myself. Okay. So we have a linear system. We have the associated homogeneous system because we set the 6 and the 9 to 0. So this is the augmented matrix for this system. We could also write the augmented matrix for the homogeneous system because you just put zeros there for that. Okay, so here's my square matrix. It's going to turn out that certain forms of this square matrix are going to allow you to answer that question. Does this have an infinite number of solutions or one solution? And it has a certain property. And that property is the following. A square matrix like this is non-singular if it's the matrix of coefficients, right? Matrix of coefficients of a homogeneous system with a unique solution. So we can have, so it's non-singular. If this thing has one solution. So the words are, it's long, right? It's non-singular if the square matrix is non-singular, if it's the matrix of coefficients of a homogeneous linear system that has one solution. That means no free variables, right? So it's actually just a word saying it's a linear system. It's a certain kind of linear system with no free variables, right? And then there's the opposite side. The matrix is singular if it has an infinite number of solutions. So it's just the opposite one. Okay, it's singular if it's the matrix of a homogeneous linear system with infinite number of solutions. So that means you're going to have a free variable. So you can tell whether a system is singular or not by reducing it to echelon form and finding out whether it has any free variables. Now, you may have heard the word singular and non-singular before in a different context with matrices, and you may realize that there's something called determinants that if a determinant of a matrix is 0, then it's singular, and if it's not 0, it's non-singular. So you may know that. So for this chapter, you have to forget that. I'm going to ask you some problems. Are matrices singular or non-singular? You can say, well, I can just find a determinant. Well, no, you can't. Well, you can, but then I won't give you any credit for it. Because what I want you to do is use the definitions of singular and non-singular in this context. Because there are going to be two different definitions that will end up doing the same thing, but you don't want to jump the gun. We want to know why there's two different things that provide the same information in different contexts. So all the way through, we'll see this as a thread of singular and non-singular square matrices. And I only apply to square matrices, sort of picking up these different properties, which are very special. Okay. So that is, and one of the problems is to ask you, I give you two matrices and ask you which one's singular, which one's non-singular, and you don't compute the determinant. If you know what that means, you go, and we have a chapter later on about determinants, but you go and you say, okay, well, it's going to be singular. I take the matrix. Like if I give you a matrix like this, let's say I have 4, 8, 14, and I want to know, is this singular or not? Well, what you do is you put this as the coefficient matrix of a homogeneous linear system, like this, and then reduce it to echelon form. say, minus 2 row 1 plus row 2 is going to be 0 because minus 2 times 4 is minus 8, and that cancels that. And you have minus 2 times 8 is minus 16. Minus 16 plus 14 is minus 2. So you look at this and you can see that, okay, well, y is leading, x is leading, no free variables. So this matrix is non-singular. Okay, and then, but if you had the matrix instead, you had 4, 8, say, 12, 24, you would do the same thing, 4, 8, 12, 24, 0, 0, and then you would do the same minus, say, 3 row 1 plus row 2 to find 4, 8, 0, and then that would give you 0 and 0 and 0, hopefully. And then you have a free variable, so it is singular. Because infinite number of solutions, because you have a free variable. So the logic of the solution is, to answer the question, is this singular? You look at the linear system, the homogeneous linear system, solve it, reduce it to echelon form, and then you have to solve it. You just answer the question, okay, is there a free variable? Yes. Then there's an infinite number of solutions, therefore it's singular. Or no, there's no free variable, so there's one solution, so it's non-singular. So that's just then you sort of, that's what you want to do, like on the homework problem for this issue. Okay, that is what's going on with that. And there's more stuff in the text that does this, and we will practice this. But I want to, like, here's some examples, which one of these singular and non-singular. Okay. Maybe we can practice one thing before going on. We should. Because there's a problem here that maybe sometimes I forget to introduce in class. And let me